beta is inside the circle. The viable solutions for the one norm is inside this diamond. Okay. But now, if I didn't have this restriction on beta, my solution would be this two-dimensional point over here. Right? So we're going to think of the data as going to kind of be living out here, and the closest point on the board is going to be right at this point here. Okay, so now I want. So y is going to live here, and I want, or I don't know. So now I want the closest point inside here, inside of these balls from this from the solution. Okay, so now if I draw this, the solution for the ridge regression is going to essentially be a circle centered around A. So I want the smallest distance from here. It's going to be a point that's right here. So this is the solution for ridge. It's going to be the point on the circle here. But the closest point to this this green diamond, which is going to be the result of the lasso, is going to be here. I'm going to get a circle. If I draw this circle here, right? The solution for the lasso is going to be here. It's going to be right at this corner point. Now, this corner point has a nice property that along this axis I have a value, but along the y-axis, the second axis here, it's 0. Right? It's exactly 0 along this axis. And it's because this restricted shape is kind of pointy. Okay, because I'm restricting the solution to be in this ball, I tend to find solutions on these corners. And the higher dimensional the point, the space, the more corners that this ball has, this high dimensional ball. So I'm going to be more biased towards these corners. Now, if my solution here, A, was kind of down here, then the closest point would still have no non-zeros. But for many of the possible solutions, the closest point will be on the corner. So this is kind of the interpretation of why the lassos give you a sparse solution. So what are the advantages of having a sparse solution of this regression?
I think there are a lot of things you can do with sparse matrices, like there's a store and there's easy to remember well.
So it's on the smaller to store. Okay. Good. So what did we talk about last week, Wednesday? So if we're doing this compressed sensing, we're kind of solving something with the assumption that the actual data will be sparse. And so we want to try and find a solution and bias them towards sparse solutions. And so you want to kind of plug this into the framework for doing this. So you want, if you have a solution that you're trying to find, if you have a setup you try and find a sparse solution for, like in the compressed sensing model, then trying to minimize this lasso constraint instead of the regular least squares. And there's one step in orthogonal magic pursuit where we were just minimizing these squares. Replacing it with this is going to tend to give you a sparser solution. Okay? And so the other one is that it's easier to interpret. Okay? So what you're saying is, I have some variables some values I want to explain based on some large number of variables. these variables are captured by this d-dimensional space. Right? And these could be a bunch of attributes I have about customers, and I want to try and say what is the relationship between these attributes towards these customers towards how much money they spend on my website. Well, if I have some linear model, which is a linear combination of all of the coefficients, then yeah, I kind of say ones with higher slope are more important, but I don't really know the scaling of these relative coefficients, so the slope is not really that meaningful in a relative sense. But if you have some are set to 0 and the others are non-zero, then these are saying these are the ones, these variables are alone sufficient to give a good explanation of what's going on. So I'm picking out fewer of my attributes to explain my data. I should be able to trust these more. I'm more likely to overfit my data if I'm using all of the attributes to try and explain it. If I can say, I only need these 3 or these 5 attributes to explain this data, it's much less likely I've overfit some complex model. I now have a very simple model to represent it. So it's easier to interpret, it's less likely to overfit. So one thing important to point out though is even though I may only be getting back a small number of attributes saying these are the explanation, that's not the only possible way to explain it with 3 attributes. You could have 2 attributes which are basically telling you the same thing. So say you have something like this person, if you have like what is this person's household income and then what is their individual income. Those are probably very highly correlated with each other and explain basically the same amount of information. So just because you chose one or the other doesn't mean that they're both kind of that you should have only picked one. That one was much better than the other. Maybe one was slightly better, but not completely better. So even though you may get back a small number of these things, you shouldn't say these are the only ones that matter. But these are a sufficient set to explain the data and to interpret the data. Okay, so that's just a little warning there. But you can get a very small number of features which tell you a lot about the data. Okay. So maybe I made a better case that the sparse solution should be a better solution for this, right? Anyone have doubts? They'd rather have a dense solution? Oh man, who wants to be dense, right? Okay. Okay, so we have a way of solving this linear regression with a sparse solution that also regresses towards the mean. So it's going to be less biased towards outliers. But it involves solving this optimization procedure. So how do we do this? So is this easy to solve? Okay, so I talked about on Monday, or no, on Wednesday, last week Wednesday, about a procedure I told you was not completely optimal, was not usually the best way to do things. And this was called orthogonal match and pursuit. Okay, and this was basically, I took one direction at a time, and I tried to kind of find the one most explanatory direction, and then I just repeated this over and over again, kind of in this greedy fashion. And so, even though this wasn't the right way to do it, I'm going to write this back up again because this is going to give us the right intuition of how to do this. Okay, so orthogonal match and pursuit. We're going to set this residual to be y, and then we're going to we're going to set aj equals to 0 for all j. So we're going to set all the coefficients to 0, and we're going to try and explain this y with this residual, and initially we haven't explained anything. So this residual is still all of y. And so then for I equals 1 to D or some number, we're going to repeat this. And we're going to find first the column J, which is most explanatory. So this was out of all the columns of X of C dot R. So I'm going to find the most explanatory column. So this is going to be the coordinate which is most gets me closest towards the solution. It is most explanatory. So if the dot product is the, actually this is max. So the most explanatory means if the dot product is the max, if this solution is here, this direction is pointing most towards here. This dot product, which is essentially measuring, it's kind of a transformation on an angle, if it's the smallest angle, it's the largest dot product. Okay, so the maximum dot product. Then I'm going to set AJ equals to the R min. So this will then be the J coordinate corresponding with this column of all A in R minus X. Right, so I solved this least squares solution here. To find the best explanation, I think I used a gamma here before, but then we set this as the explanation for this column. And then we're going to refactor out on the new residual as R minus AJ, right? So I subtract out what I've explained. Okay, so I found the one column that gave me the best explanation. I figure out what that explanation is, and I subtract that out of the data I'm trying to explain. And this is what I have left. And then, I repeat this for loop, either some number of steps or until this residual is empty. Or I can say until R equals to 0. So hopefully, eventually, I explain this. Excuse me. Okay, so this was the least square step here, but I don't want to do least squares. So the first change I want to make is I want to say have some alpha times A, and have this be the 1 norm. So instead of solving the least squares here now, I can just plug in this constraint for having A in here. For this extra regression term, or this extra regularization term. So this is giving me the shrinkage, and by this dual property here, I can interpret this as being inside of some ball defined by some beta, which corresponds with this alpha. I don't know what that beta is at this point, but that's going to be okay. Okay, and actually, what I can do is, and the notation gets a little tricky to try and write this, so I'll try and work through this a bit more, is instead of just solving for this 1A at a time, I can say there's some set of variables. So J is going to be the set of J1 through Ji, such that Aj is not equal to 0. Right? So I have this set of these columns which have been set, and then I can solve this actually instead. I can do something like R minus Xj, where So I can, for all the ones where I know I have a non-zero, I can try and solve for this solution here, instead of just the newest one. So I can build up a submatrix x sub j, and have these solutions, and I can resolve for these. So instead of having a greedy technique where I set this value for the jth column and then I fix it, I said, well, now that I have more columns to play with, I may come up with a different solution here. And if you plug in, if you're doing just ordinary least squares or just ridge regression, then solving this is just taking this matrix inverse. Right? So you can again solve for this. The notation is a little bit hard to write here, but you could write this up procedurally as an algorithm. Okay? So if I use the set J in here, then so doing this will give me an even better solution. Okay. But I still haven't explained how to do it with this here with this one norm. Okay? So the idea is going to be very similar to this in that I'm going to build up the coordinates that I have one by one. I'm going to add one coordinate at a time. And I'm going to do that by, instead of playing with this alpha parameter, playing with this beta parameter. And so kind of what you should intuitively be able to see is that as beta gets larger and larger, my solution is going to get more dense. If beta is set to infinity, right, then this ball will include the entire space, and I can return the least square solution. And the least square solution is going to be dense. As I shrink it, as I shrink beta, I'm going to more likely to, because the ball is going to shrink, the corner and here is going to be some kind of more likely to hit one of these corners. Whereas I grow this, eventually, at some point, it's going to be I'm going to grow this diamond so that the closest point will actually be on the edge. So as I shrink beta, I'm going to get a sparser and sparser solution. What that means is, as beta is equal to 0, I'm going to get all coordinates are going to be 0. And when beta is a little bit bigger than 0, I'm only going to have one coordinate. Okay? So I haven't fully proven this, but if you believe this, that means that the one coordinate I should pick should be the one with the largest dot product with the least square solution. The least square solution will be the one with the largest dot product with y, which the first step is r. So the first coordinate I choose is going to be the same one as I did with the orthogonal matching pursuit. Okay? So I'm going to do something similar where I'm going to... So let me try and... The algorithm is I've written, if you want to follow along in the notes, I wrote up a kind of very complicated algorithmic form. I'm going to try and kind of walk through the procedure a few rounds to give you a taste. So what I'm going to do is I'm first, and I think I use t instead of beta, but it's going to work essentially the same way. Okay, so the first thing I'm going to choose is I'm going to first find j such that xj equals the arg max of a column in x with y xj. Okay, so I'm finding this column or this coordinate axis which has the most explanatory power of y. Okay? And then I want to say as I increase beta, so now instead of writing r as equal to y, I'm going to write r as a function of beta. Okay? So I'm going to, and this is now going to have some nice structure to it. So it's going to have the property that r equals to 0 is going to be 0. So if beta is equal to 0, then my solution, I'm just going to return 0. So this is not interesting. When beta is small, I'm going to return some coefficient along this vector here. Okay, so when beta equals small, then our beta is going to be equal to y minus xj times beta. Okay, so why is this true? So I said I could have the norm of the ball be within the norm of my solution be within a ball of magnitude beta under the L1 norm, but I only have, at the first point, I only have one coefficient, so it's growing along this axis. So if it's going to be the closest point in the ball, it's going to be along this coordinate axis at exactly a length of beta. So my first coefficient, the only one I'm using, its value was aj, but now that aj was going to be beta exactly. Okay, so actually what I'm going to do is I'm going to write this as y minus j equals 1 to d of xj times aj as a function of beta. Okay, so, and what this looked like is this aj for the first part, this was all zeros except for the jth coordinate, and the jth coordinate was chosen here, so that this would be, let's call this j1, this is j1, then here, then then this was this vector a, which is equal to a1 equal to 0, a2 equal to 0, aj1 is equal to beta, and the rest ad equals to 0. Okay? So that's here, and then in the future, I'm going to set other ones of these to be non-zero. But it's not going to be quite as simple as just setting them equal to beta. It's going to be something where the sum of them is going to be equal to beta. Okay, so in fact, this will be, just doing this will be the right solution up until some point. And at some point, I can grow this ball. And so what's going to happen is that there's going to be some special point. I draw this, so this will be at a 45 degree. And when I get to this point here, then this L1 ball is going to look like this. As I continue growing this, then this 45 degree angle thing will be the closest point on this edge will be projected at a 45 degree angle. So if I go past here, the closest point is going to be right here, and it's going to involve the second coordinate. So as I keep growing this ball, at some critical point, I'm going to want to use a second coordinate to explain this. And so I can actually solve for this value. So the nice thing is that at every point, this residual, as a function of beta, is going to be this linear equation. And so this is a linear equation. This is a linear equation of beta. Right? So this is kind of just a linear expression, and this is y minus this. Right? And what I want to do is, to solve when using this r, I'm going to have that you want to solve for where the magnitude of xj1 r of beta is equal to the magnitude of xj2 r of beta. Okay, so both of these are these linear equations, and I'm not going to go through how to do the algebra, but you could work it out so that you can solve for each other value of j, where these become equal. And this is exactly this point here, where you need to start moving also along this other coordinate direction. So now you're going to be increasing. Now so now I want my solution to be along this direction. So I can solve for all other values j where this happens, and then and this is a linear expression, I can use linear algebra to do this, and then I can start kind of having these coordinates after this special point be as a function of have non-zeros in two different locations. So what happens then after this happens, then you kind of have aj1 of beta is going to be equal to and so this will happen at beta equals to some point I call we'll call this beta 2, and so this will happen at a so I have an expression, a linear expression for a as a function at beta 2. This was the old linear expression for a that I had solved for before, plus beta minus beta 2 times my new this is times a new slope for B1, and I'm going to have aj2 of beta equals to beta minus beta 2 times this slope for B2. So then once at this point, I can then solve for what the slope should be using, again, some linear algebra, so there's some details to do this, and then for, so these are the values for alpha aj1 and aj2 for beta greater than beta 2 and less than some beta 3 I haven't found yet. So there are these critical breakpoints where this changes. Okay. So I definitely have not gone through all the details. I don't expect you to kind of fully understand, but hopefully kind of get the idea of how you can solve for these critical points where this changes, and then we solve for these new coordinates by again doing something like this orthogonal magic pursuit with the larger value of beta. And you can kind of push this forward and solve for the solution for A for all values of beta, and it becomes this piecewise linear formula. Okay, and so this approach is called least angle regression. So you know the whole procedure is pretty complicated. So I'm not going to go through the details. If you want to look it up, there's an excellent book called Elements of Statistical Learning. Statistical Learning, and it's free. There's a free PDF online. This is by a bunch of people from the statistics department at Stanford, and it's linked off of the webpage. And this goes into a lot more detail about the rationale and how to compute this. Okay, but there are a couple of points so I want to bring up that are important things to emphasize in this algorithm. Okay, so the first one is that I had solved for all values of beta, and likewise all values of alpha. Okay? So I didn't just give you one solution for all the coordinates A. I gave you a solution starting all the way from all zeros that will eventually take some path and reach this least squares solution. Okay, so which solution should I use?
What do you mean by which solution?
Well, I've given you many different values for A here, right? So at every step of this procedure, for every value beta, I return a vector A. It starts out for a small beta, it's almost all zeros. For a very large beta, it becomes dense. It becomes exactly the same as the least squares solution. And so each of those corresponds with a different value alpha. So I posed the problem. I said, you're given an alpha, and then you solve for this. And I tried to argue that for the regression to mean that there was some solution where I should shrink this towards the mean a little bit that was better than the least squares solution, because outliers tend to pull it away from the mean. Right? I should somehow shrink to the mean, but I don't know what this mean is, right? I don't know what the true value is. So what should I do?
How would the first beta and negative?
I'll return the first beta value, so slightly bigger than 0.
Yeah.
Oh, well, maybe, but so not always. So that'll give me a very sparse solution. I'll say, here's one thing that explains it, but I'm not even going to give you a very good explanation. It's just along this direction. So kind of the important point is I already solved for all of these values. So I have all these values available. So the trick is I want to use, so I want to use cross-validation, okay? So I don't want to actually solve it on my full data set. Before I started, I should have randomly removed some of the data points and solved for my solution with the subset of the data. This will be called the training set. Okay? And then I've got this leftover data, which I also want to minimize the error. And for those, I can check how well I did. Those are randomly taken out. And so for those that I took out, I can see how well I actually minimized this least squares error. That's what my goal kind of was. I use this regularization term to kind of deal with outliers, but I actually want to minimize this least squares term. So I can use my test data to train this, and I get every possible solution for every value beta, which means for every value alpha. And then as I'm doing this, it's a linear expression, so I can keep figuring out what is the least squares value for, on the remaining data. And I can use that to tell me where, whichever one minimizes that, that's where I should stop. So probably, as you see, if you return the solution right at 0, this is not going to be very useful. And if I return it the least squares, I probably have overfit the data a little bit. Somewhere in between is going to be a good place to stop. And I'll let the rest of my test data tell me. Yeah.
So does the algorithm contain that cross-validation step, or is that something?
So that's another layer on here I didn't explain because it would have made it even more confusing. But you need to do this, instead of starting with all of the data, you pull some data out initially and save that for later. And then the data you kept as the training data, you run that, and while you're doing that, you're calculating it. So you don't stop actually until you reach the least squares solution. And the whole way you maintain the minimum on your test data. And and then once you're done, you go back and say, I'm going to return the solution for the minimum of the test data. So that's another layer to add on. So there's one other thing I didn't quite mention. So this is called least angle regression. There's kind of a slight variant that I'll try and describe, and you may not grasp this difference, but there's kind of this strange thing that happens where if you're solving for these coordinates, so you start with 1 and then you get two of the coefficients. Initially, when you just have 1, this coefficient is 1, and then these coefficients have a sum equal to beta, right? Oh no, these coefficients have a sum equal to 1. Well, one of them might be actually negative. At some point, one of these coefficients will be negative. This could happen, and this does happen in practice. And so this becomes kind of strange. What happens is sometimes when it's negative, that means this coefficient would grow to a certain value, and then it will start shrinking again. And eventually the coefficient may hit 0. Now this was not a critical point where you found a new coordinate to solve, but you can again snap this value to 0. And so this turns out to be, you need to snap this value to 0 if it hits 0 and check for this condition. And this is the one that actually will provably give you the right answer here. If you don't do that, you will kind of overshoot and have this coefficient be negative when it should be positive. So it could be that the coefficients initially are actually negative. If A was actually over here, then the initial coefficient would be negative. That's fine. But if it becomes negative and then goes back, hits 0 again, and is going positive, at that point you want to snap it to 0. The problem with this is that although, if you only make them non-zero once, this will clearly terminate after D things have become non-zero. So there's the complexity of this becomes bounded. If you can set them to 0 again and then have to resolve for this equation, there's this very recent kind of crazy result that you could go through essentially an exponential possibility set of